Let's go for derivation. Consider two cells of EMFs E1 and E2 and internal resistance R1 and R2 connected in parallel between the 2 points B1 and B2 as shown in the figure. So here between the B1 and B2, let us assume that V is the potential difference. V is the potential difference between B1 and B2. Because of the parallel combination, even the potential difference between the first cell is also V volts and the potential difference between second cell is also V volts. Okay. Therefore, we can write the expression V is equal to epsilon 1, that is the EMF of the first cell minus the current currents driven by the first cell into internal resistance. So, let us assume that is the equation 1. Because the potential difference is same between the two cells, we can write it as V is equal to EMF of the second cell minus current sent by the second cell and internal resistance. So, that is R2, it is R2, okay. It is R2, right, R2, yes. Next, okay. So, now let us solve these equations 1 and 2 for the currents. So, I1, so by using the first equation you can solve the equations for I1. So, send the I1 R1 to the right hand side, you will get this equation, and V to the right hand side and I1 R1 to the left hand side. So, you will get I1 R1 is equal to epsilon 1 minus V, I1 is equal to E1 minus V by R1. Similarly, you can solve this equation for I2. Similarly, you will get I2 is equal to E2 minus V by R2. It is found that, so the total current in the circuit is given by I is equal to I1 plus I2. I1 plus I2. Already we have shown here that the two currents combine to form the current I1. So, therefore, you can write this equation I1 is equal to I1 plus I2. Now, substitute the I1 I1 instead of I1 in terms of EMF of the first cell and internal resistance. Similarly, for I2 you can substitute. Now, you can separate this into two fractions, E1 by R1 with the same sign minus V by R1, and then again convert this into two fractions, E2 by R2 minus V by R2. Then rearrange so that the EMFs let it come together and the internal resistance and voltage is come together, but here the minus sign has taken common factor. The minus sign has taken common factor, and even not only minus sign, this V also can be taken common factor outside. So, you will get this equation, and you can simplify this by taking the LCM. So, multiply E1 R2 plus E2 R1 divided by R1 into R2. So, you will get this equation. That is how to add the two fractions. Similarly, you can add these fractions also. 1 by R1 plus 1 by R2 is equal to 1 into R2 plus 1 into R1, that you will get R2 by R1 divided by R1 into R2. Name this equation as the equation 4. Equation 4. Now, now stop here and go back to the equivalent circuit. What is the equivalent circuit? So, instead of this arrangement, you can write an equivalent circuit. Equivalent circuit. let us replacing between the points A and C, a single cell is replaced, okay, such that the single cell sends the same current in the external circuit I. Okay. Let the single cell's equivalent resistance be E equivalent and let its internal resistance be R equivalent. So, we have to derive the expression for this E equivalent and R equivalent. So, of the two cells when they connected in parallel. Okay. Now, let us come back to this. Now, let us come back to this. Okay. So, write the same expression. Let us assume that V is the potential difference, same potential difference across the points B1 and B2. You can write therefore V is equal to equivalent EMF minus current into equivalent internal resistance, and again solve this for the current. So, you have to solve this for current. So, send this term to this side and V to this side, and therefore, it becomes IR equivalent, okay, is equal to E equivalent minus V, divide throughout by these R equivalent. So, here you will get I, and here equivalent by R equivalent minus V equivalent by R equivalent. Okay. Yes, you can write it slightly this as a V into 1 divided by R equivalent. Let us take this equation as a phi, equation as phi. Yes. Now, let us come back, okay, to the place what we have derived for the current in the combination, current in the combination. Okay. So, now write the equation 5 below the equation 4. Equation 4. It is found that these two equations are equivalent equations. Equivalent equation. So, both the equations left hand side is I, and both the equations have a constant V. So, hence equation 4 and equation 5 are called as equivalent equations, and this is possible only when the so different terms are equivalent. For example, these two terms must be equal and the coefficient of V must be equal. So, the equation 4 and 5 as left hand side is equal, this implies that by comparison you can write E equivalent by R equivalent is equal to E1 R2 plus E2 R1 divided by R1 into R2. Now, again separate this into two fractions, fraction number 1 plus fraction number 2. Okay. You will get so E equivalent by R equivalent is equal to E1 E1 R2 and right. So, finally, we will get E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Yes, this is an important equation. So, let it name the equation as equation number 6. Okay. Now, compare the other part. So, what is the other part? You can compare in the equation 4 and 5 that 1 by R equivalent can be written as R2 plus R1 divided by R1 into R2. So, R1 into R2. Yes. So, right. Yes. So, you can just write 1 by R equivalent as 1 by R equivalent is written as R2 plus R1 divided by R1 into R2. You can just write it as okay. Now, this equation you can separate it. So, again you can separate this into two fractions. If you separate this into two fractions, R2 get cancels, okay, you will get 1 by R1 and R1 get cancel in second equation, you will get R2. So, therefore, you can write from this equation. So, you can write this equation 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Okay. So, you can call this as equation 8. Maybe the order is slightly different. So, you can just understand how these equations are obtained. Now, by reciprocal, by taking the reciprocal, you can say that, okay, you can say that R equivalent can be written as, okay, 1 R1 R2 divided by R1 plus R2. Now, just cross multiply this, cross multiply that. So, let it be come over here. R equivalent divided by R1 R2 is equal to 1 divided by R1 plus R2. Okay, 1 divided by R1 plus R2. So, you will get this equation from this. Now, let us go back. Okay, let us go back, and here you have got this equation. Okay, where is that? Yes, this equation. This equation you have got. I want to replace here R1, R2 and R equivalent. I want only E equivalent. I don't want this R equivalent and R1, R2. How can I replace this? Okay, just cross multiply this here. You will get here R equivalent divided by R1 into R2. That we can replace. Okay, that we can replace. So, here, okay, as R equivalent divided by R1 R2 as just okay, yes, just okay, yes, this has been cross multiplied here and you have got this. This has been taken separately. Observe carefully. Okay, these are the changes we have made. So, therefore, instead of this, okay, you can just write 1 divided by R1 plus R2. 1 divided by R1 plus R2. Yes, this is the final equation. This is the final equation. E equivalent is equal to E1 R2 plus E2 R1 divided by R1 plus R2. Okay, R1 plus R2, right. Next, R equivalent can be written as R1 R2 divided by R1 plus R2. And another equations which you have already derived, which is more, okay, can also be written as E equivalent by R equivalent is equal to E1 by R1 plus E2 by R2. Yes. So, these are the derivations of the E equivalent and R equivalent. So, E equivalent and R equivalents we have derived like this. This can be applied to a 3 or more cells connected in parallel. If 3 or more cells are connected in parallel, then you can use a slightly different equation. So, you can use E equivalent by R equivalent as E1 by R1 plus E2 by R2 plus E3 by R3. So, this is an equation. And how can you write R equivalent? Directly we can't write R equivalent. So, 1 by R equivalent can be written as 1 by R1 plus 1 by R2 plus 1 by R3, where R1, R2 and R3 are the internal resistance of the 3 cells. When the 3 cells are connected in parallel. Okay. So, these are the effective resistances and effect. Okay, students, let us consider another case where n number of cells connected in parallel to each other. If all of them have same EMF E and same internal resistance R, just like as shown in the figure, they have arranged in parallel combination. This combination is driving a current I. Now we have to derive an expression for equivalent EMF of this combination and equivalent resistance, equivalent internal resistance of this combination. Here n cells are connected in parallel. Let us take the case of two cells when they are connected in parallel. We have found that its equivalent resistance can be written as E1 R2 plus E2 R1 divided by R1 plus R2. Now, if both the cells have same EMF E and same internal resistance R, then this equation becomes E equivalent is equal to ER plus ER divided by R plus R. So, that becomes 2 times the ER divided by 2R. Yes, cancel 2, 2 and R. So, that comes down to equivalent EMF of two cells of same EMF is just the EMF of a single cell. The equivalent EMF of two cells when connected in parallel, the equivalent EMF is nothing but EMF of the single cell. Similarly, if 3 cells, 4 cells, 5 cells are connected in parallel, each having the same number, same amount of EMF, we can write that equivalent EMF is equal to the EMF of a single cell. Suppose if 1.5 volts cells are connected in parallel, some 10 cells are connected in parallel. What is the equivalent EMF of this combination? It is just the 1.5 volts. So, hence equivalent EMF for this combination is just a EMF of a single cell. Now, let us draw the expression for internal resistance equations just we have derived for parallel combination. That's 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This time let us take for n number of cells. The last internal resistance of the cell let be Rn. If all of them have same internal resistance, we can write 1 by R equivalent is equal to 1 by R plus 1 by R plus 1 by R, like that n times we can write. So, if you add them, it will be equal to n times the 1 by R. Therefore, 1 by R equivalent is equal to n times the 1 by R. From this we can write R equivalent is equal to R by n. So, that means the if internal resistance of a single cell is R, it get decreased n times. So, that means greatly internal resistance is reduced. This is the advantage of the cells connected in parallel. If the internal resistance of the cells are very high, it is greatly reduced. Now, just write down the equivalent resistance of this combination, each having the same internal resistance as R by n. Now, let us assume that this combination is connected to an external circuit of resistance capital R. That's this combination of n cells in parallel, each having same EMF and internal resistance, are connected to an external circuit R. So, and it sends the current I. Let this combination sends the current I. Now, we have to write the expression for the current of this parallel combination. We already know that the current in a circuit can be written as the ratio of total EMF to the total resistance. That includes the total resistance includes the external resistance plus the resistance offered by the cells in combination. So, as we have already learned, the total EMF is just the EMF of a single cell, and denominator external resistance plus equivalent internal resistance, R equivalent, that is R equivalent. You can substitute R equivalent. Now, R plus R by n. R by n. Yes. In denominator, it's a number plus fraction. You can just add these two fractions. So, you can just write R by 1 and simplify this R into n plus 1 into R divided by 1 into n, that is n. Now, make it as a single ratio. So, n goes to numerator, therefore, the current sent by this combination is equal to n times the EMF of a single cell and nr plus a small r. Okay. So, this is the expression for the current of this kind of combination. Let us assume if internal resistance is very much less when compared to the nr, n times the r, okay, n times the r. If r is very small, negligible, okay, you can neglect that in the denominator. Then the current will be equal to Ne divided by just n into capital R. N get cancelled. That gives rise to a current is equal to EMF of a single cell divided by just the external resistance. It looks like that the current is produced by a single cell. If a single cell sends the how much current, if you connect all the cells in parallel, the same current flows through the external circuit. Then what do you think of the reason for connecting so many cells in parallel? Okay, if they send the same current as a single cell, 1.5 volts sends the same current. If 1.5 volts connected in 1.5 volts are connected in parallel, that also sends the same current. Then what is the use of connecting the 10 cells in parallel? It is found that the chemicals in them get added up, and that combination sends the current for a long time. For example, if 1.5, if every cells can be used for 1 month, if you take 5 cells or 10 cells, you can use it for 15 months, okay, like that. Okay. Yes. So, this is about the derivations of the cells in combination. Okay. Now, let us take up another case when the cells are connected in series. In this case also assume that let all the cells have a same EMF and same internal resistance. So, write the cells in series. Let there be n number of cells, each having the same EMF E and same internal resistance R. Then what is the expression for equivalent EMF? Okay. It is found that while doing the derivation of series combination, total EMF is equal to sum of the individual EMFs. So, if all of them are same, okay, you can just add n times. So, you will get E equivalent is equal to n times the EMF of a single cell. Similarly, we have derived that R equivalent is the sum of the individual resistance, because they are all connected in series. When they are connected in series, their resistance gets added up. So, R equivalent becomes just n times the resistance of individual internal resistance of individual cell. Yes. By using these two equations, you can derive the expression for the current sent by this combination when it is connected to an external circuit R. Okay. Use the same equation. EMF is equal, current is equal to total EMF divided by total resistance in the circuit. Okay. Yes. So, equivalent EMF divided by external resistance plus R equivalent. Now, substitute for the equivalent EMF n times the E. It's n times the EMF of a individual cell divided by R plus NR. Yes, students, this is the final expression for the current when the cells, when large number of cells connected in series, each having the same EMF and internal resistance. Okay. Yes, in our videos we have derived, okay, all these cells in combination. Okay, thank you very much students for watching. Your subscription is very much needed. Okay, I'll request you to make the subscriptions 1000 as early as possible.